In a couple of billion years, our sun will become so violently hot that it could extinguish all life throughout the solar system. Yet, as it intensifies, it might also render distant worlds like Pluto and Saturn's moons habitable for the first time. How can the center of our solar system be simultaneously so generous and so destructive? This is the complete story of our sun, from its violent birth in the depths of space to its eventual transformation into something unrecognizable, spanning billions of years of cosmic evolution. 4.6 billion years ago, the first outlines of our solar system began to emerge from the darkness. The seeds of new life sprouted from the remnants of older stars that had exploded in catastrophic supernovae, scattering their enriched elements across the void. A colossal cloud of dust, gas, and vapor materialized in this region of the galaxy, spanning trillions of kilometers. This nebulous mass contained all the raw materials that would eventually become our sun, our planet, and every atom in our bodies. The gaseous cloud began to collapse under the relentless force of gravity, drawing material inward from all directions. As it contracted, it started to rotate, slowly at first, then faster as conservation of angular momentum took effect. The rotation caused the cloud to flatten, transforming from a roughly spherical shape into a spinning disk. At the center of this disk, a dense core formed as matter accumulated, growing more massive with each passing millennium. Meanwhile, the rest of the cloud had flattened into a protoplanetary disk that rotated around the central concentration. Within this disk, smaller aggregations of dust and gas began gathering together through gravitational attraction and collision, forming the initial building blocks of what would become our planets. These planetesimals grew larger over time, sweeping up material in their orbital paths. The dense core at the center began to heat up as gravitational compression converted potential energy into thermal energy. It started to glow with a dull red light, barely visible through the thick envelope of surrounding gas. The pressure mounted as more material fell inward, and this marked the birth of a protostar, the infant precursor to our Sunday. This embryonic star consisted primarily of hydrogen and helium, the simplest and most abundant elements in the universe. If you could have witnessed the protostar during its earliest days, it would have appeared quite dark and obscured by the dense clouds surrounding it. The protostar was not yet generating energy through nuclear fusion, but rather through gravitational contraction. It was warm, but not the blazing furnace it would eventually become. Within the first 10 million years of the solar system's formation, the gas giants began to take shape. Jupiter, Saturn, Uranus, and Neptune formed in the outer reaches of the protoplanetary disk, where temperatures were cold enough for volatile compounds like water, methane, and ammonia to condense into ice. These planets grew massive by accumulating enormous atmospheres of hydrogen and helium from the surrounding nebula before the solar wind eventually cleared away the remaining gas. Inside the protostar, the temperature and pressure continued to climb relentlessly. The core grew hotter as gravitational energy heated the collapsing material. Finally, after approximately 50 million years, something extraordinary happened. The infant protostar reached the critical threshold where pressures exceeded 100 billion times Earth's atmospheric pressure and temperatures soared past 10 million degrees Celsius. At these extreme conditions, hydrogen nuclei possessed enough kinetic energy to overcome their mutual electromagnetic repulsion and collide with sufficient force to fuse together. 4 hydrogen atoms combined through a series of reactions to form a single helium atom. The mass of the helium atom was slightly less than the combined mass of the 4 hydrogen atoms, and this missing mass was converted directly into energy, according to Einstein's famous equation. This process, called nuclear fusion, released tremendous amounts of energy, and our sun was truly born. The ignition of nuclear fusion marked a fundamental transition. The protostar became a main sequence star, joining billions of similar stars throughout the galaxy. The outward pressure from fusion reactions balanced the inward pull of gravity, creating a stable equilibrium that would persist for billions of years. The solar wind intensified, blowing away the remaining gas and dust from the inner solar system. Over the following tens of millions of years, the rocky planets Mercury, Venus, Earth, and Mars formed closer to the Sunday. In these warmer regions, only materials with high melting points could condense into solid form. Metals and silicate rocks accumulated into planetesimals that gradually assembled into the terrestrial planets through countless collisions and mergers. The Sun entered its childhood as a stable main sequence star. It was now consuming 603 billion kilograms of hydrogen every single second, converting it into helium through fusion reactions. The energy released in just 1 second of this process would be sufficient to power every household on Earth for approximately 800,000 years. The sheer scale of this energy production is almost incomprehensible. The Sun is incredibly hot by any terrestrial standard. The visible surface, called the photosphere, maintains a temperature of approximately 5,500 degrees Celsius, hot enough to vaporize any known material instantly. But this is nothing compared to the core, where temperatures reach an estimated 15 million degrees Celsius. At these temperatures, matter exists in an entirely different state. As a plasma where electrons are stripped from atoms and nuclei move freely. The Sun began its life with enough hydrogen fuel to sustain fusion reactions for approximately 10 billion years total. It is by far the single largest object in our solar system, containing 99.86% of the system's total mass. Approximately 1.3 million Earths could fit inside the Sun's volume. Its diameter spans 1.4 million kilometers, over 100 times that of Earth. If the Sun had formed with less mass, Earth would have faced catastrophic consequences. Consider what would have happened if it had become a brown dwarf star instead. Brown dwarfs are failed stars, objects too small to sustain stable hydrogen fusion in their cores. They form when a collapsing cloud contains insufficient mass to reach the critical conditions for fusion. Brown dwarfs can generate some heat through gravitational contraction and may briefly fuse deuterium, but they never achieve the sustained fusion of ordinary hydrogen that characterizes true stars. Without a proper star providing steady heat and light, Earth would have frozen solid within a few million years. Temperatures would have plummeted to perhaps minus 200 degrees Celsius or lower. Any water would have frozen into solid ice, and the atmosphere itself might have condensed and fallen to the surface. Life as we know it would never have emerged in such a frozen wasteland. Fortunately for us, the Sun contained sufficient mass to ignite nuclear fusion and become a proper star. This allowed it to radiate heat and electromagnetic energy consistently, creating a stable environment where liquid water could exist on Earth's surface. This stability was essential for the origin and evolution of life over billions of years. The Sun's core is a realm of extraordinary conditions where nuclear fusion reactions occur continuously, releasing energy equivalent to 15 billion atomic bombs every single second. With such tremendous forces at work, you might wonder why the Sun doesn't simply explode from all this energy. The answer lies in a delicate balancing act that has persisted throughout the Sun's lifetime. This balance is known as hydrostatic equilibrium, a state where two opposing forces precisely counteract each other. Imagine a tug of war between two perfectly matched teams. If each team pulls with equal force on the rope remains stationary despite the tremendous forces acting on it. Something similar occurs within the Sun at every moment of its existence. The first force is gravity, which pulls all the Sun's mass inward toward the center. Every atom in the Sun attracts every other atom gravitationally, and for an object as massive as the Sun, this creates enormous inward pressure. If gravity acted alone, the Sun would collapse in on itself within minutes, compressing all its mass into an incredibly dense core. The second force comes from the energy released by fusion reactions. As hydrogen fuses into helium in the core, it releases energy that heats the surrounding plasma to extreme temperatures. This thermal energy causes the plasma to expand, generating outward pressure that pushes against gravity's inward pull. The pressure from thermal expansion acts throughout the Sun's interior, supporting each layer against the weight of the layers above it. These two forces, gravitational compression and thermal pressure, are nearly perfectly balanced. The Sun neither collapses nor explodes because the inward and outward forces equal each other at every point within the star. If the fusion rate were to increase even slightly, the additional energy would cause expansion and cooling, which would then slow the fusion rate back down. Conversely, if fusion slowed, the core would contract and heat up, accelerating fusion again. This negative feedback mechanism maintains stability automatically. By this point in the Sun's history, our entire solar system had completed its first full orbit around the center of the Milky Way galaxy. This journey takes approximately 230 million years and is sometimes called a cosmic year or galactic year. In this time, the solar system traveled at a speed of about 828,000 kilometers per hour relative to the galactic center, covering a distance of roughly 1.8 trillion kilometers. The young Sun at this stage was only 70% as luminous as the Sun we observe today. This might seem paradoxical since we often think of stars as brightest in their youth, but for main sequence, stars like the Sun, luminosity actually increases gradually over time. The young Sun emitted less total energy and appeared dimmer than the modern Sun, though it was burning hydrogen at essentially the same rate. For the next 4.5 billion years, the Sun continued at this steady pace, maintaining its hydrostatic equilibrium while gradually changing in subtle ways. Because the Sun remains in balance between gravity and pressure, the nuclear fusion reactions proceed at a relatively constant rate without dramatic fluctuations. To a casual observer, the Sun might seem virtually unchanging during this vast span of time, an eternal beacon providing light and warmth to the planets. However, this appearance of stability is somewhat deceiving. One crucial parameter was changing very gradually throughout these billions of years, and this change would eventually have profound consequences for Earth and all life upon it. The Sun was slowly growing brighter and more luminous as it aged. Why does the Sun's brightness increase over time? The answer relates to the helium accumulation in the core. As hydrogen fuses into helium, the number of particles in the core decreases. 4 hydrogen nuclei combine to make one helium nucleus, reducing the particle count by a factor of 4. With fewer particles, the core must contract slightly to maintain the pressure needed to support the overlying layers. This contraction increases the core's density and temperature. The higher temperature causes fusion reactions to proceed more rapidly, releasing more energy. The increased energy output makes the Sun more luminous. This effect is gradual, but relentless. The Sun's luminosity increases by approximately 1% every 100 million years, a change far too slow for humans to perceive directly, but significant when accumulated over geological timescales. 1% every 100 million years might sound trivial, but consider that the Sun has existed for 4.6 billion years. Over this time, its luminosity has increased by roughly 30% compared to its initial brightness. This seemingly modest change has had profound effects on Earth's climate throughout geological history. Early Earth received 30% less solar energy than today, yet geological evidence indicates Earth had liquid water on its surface even then. This apparent paradox, called the faint young Sun problem, suggests Earth's atmosphere was very different in the distant past, likely containing much higher concentrations of greenhouse gases that trapped enough heat to compensate for the dimmer Sunday. Another crucial change occurring within the Sun is the steady accumulation of helium in the core. Every second, fusion reactions convert millions of tons of hydrogen into helium. Unlike hydrogen, helium does not undergo fusion under the conditions present in the Sun's current core. The helium simply accumulates, gradually building up like ash in a fireplace. This helium will play a critical role in the Sun's future evolution, but for now, it simply grows more abundant as billions of years pass. We arrive now at the present day, 4.6 billion years after the Sun's formation. The Sun has reached middle age, approximately halfway through its main sequence lifetime. The modern sun is 30% more luminous than the young sun that first illuminated the early solar system. Its fusion reactions continue unabated, converting hydrogen to helium at a prodigious rate. Will these fusion reactions continue forever? Can the sun burn indefinitely? The answer, of course, is no. The sun contains a finite amount of hydrogen fuel. Although this supply is vast beyond human comprehension, it is not infinite. The sun has approximately 5 billion years of hydrogen fuel remaining before it exhausts the supply in its core. Most humans alive today will never witness the sun's death. Neither will their descendants for countless generations to come. The timescales involved are so vast that human civilization, indeed our entire species, might evolve into something unrecognizable before the sun enters its death throes. But the laws of physics are inexorable, and the sun's fate is ultimately sealed by the finite nature of its fuel supply. The sun's mass plays a crucial role in determining its lifespan and fate. If our sun had formed with 10 times more mass, it would have burned through its hydrogen much more rapidly and died far sooner. Massive stars burn hot and bright, but their lives are correspondingly brief. A star 10 times more massive than the sun would exhaust its core hydrogen in merely 20 million years or so. Such a star would have died long before life emerged on Earth, which required hundreds of millions of years to develop even primitive single-celled organisms. Complex multicellular life took billions of years to evolve. We would never have existed if our sun had been significantly more massive. Conversely, if our sun had formed with half its actual mass, it would have become a red dwarf star. Red dwarfs are the most common type of star in the galaxy, and they are remarkably long-lived. A red dwarf can continue fusing hydrogen for 80 to 100 billion years or even longer, far exceeding the current age of the universe. However, red dwarfs are much dimmer and significantly cooler than our Sunday. A red dwarf's habitable zone, the region where liquid water could exist, lies very close to the star. Planets in this zone would likely become tidally locked, with one side perpetually facing the star and the other in eternal darkness. The prospects for life around red dwarfs remain uncertain. Our sun occupies a fortunate middle ground. It is massive enough to burn brightly and provide ample energy for life, yet small enough to remain stable for billions of years, giving evolution sufficient time to produce complex organisms. We should appreciate the approximately 10 billion total years our sun will exist as a main sequence star. Let us now journey forward into the future to witness the sun's evolution in its later stages. We advance 600 million years beyond the present day to a time when the sun is 5.2 billion years old. The sun's luminosity has increased by approximately 6% compared to today. This might seem like a modest change, but the consequences for Earth will be severe. The increased solar radiation reaching Earth will have catastrophic effects on the planet's climate and biosphere. As temperatures rise, the rate of chemical weathering of rocks increases. This weathering process consumes carbon dioxide from the atmosphere as the gas dissolves in rainwater and reacts with minerals in rocks. The carbon becomes locked in carbonate minerals and is eventually subducted into the mantle through plate tectonics. Under normal circumstances, volcanic activity releases carbon dioxide back into the atmosphere, maintaining a balance. But as the sun grows brighter and Earth grows hotter, the weathering process accelerates while volcanic output remains roughly constant. The net result is a gradual decline in atmospheric carbon dioxide concentration. Carbon dioxide is essential for photosynthesis, the process by which plants convert sunlight into chemical energy. Most plants require carbon dioxide concentrations of at least 150 parts per million to photosynthesize effectively. As CO2 levels drop below this threshold, plants will begin to die off across the planet. First to go will be plants using the standard photosynthetic pathway. Some specialized plants can survive at lower CO2 concentrations, but eventually even these will fail. The death of plant life will trigger a cascade of extinctions throughout the food chain. Herbivores will starve as their food sources disappear. Carnivores will follow as prey animals die off. The intricate ecosystems that have developed over hundreds of millions of years will collapse within a few tens of thousands of years, a geological instant. The only places where life might persist will be in the oceans, particularly in deep-sea environments near hydrothermal vents. These specialized ecosystems rely not on photosynthesis, but on chemosynthesis, deriving energy from chemical reactions involving hydrogen sulfide and other compounds dissolved in the superheated water emerging from the vents. These organisms might survive the death of the surface biosphere for some time, but their days are numbered as well. We advance another 400 million years into the future, to an era when the Sun has reached an age of 5.6 billion years. The Sun is now 10% more luminous than in the present day. The denser helium accumulating in the core has caused fusion reactions to run hotter and faster, increasing energy output. Earth has been transformed beyond recognition. Surface temperatures on Earth have risen dramatically, perhaps exceeding 100 degrees Celsius on average. The planet has entered a runaway greenhouse effect, similar to the conditions on Venus. The oceans are beginning to evaporate in earnest as the heat vaporizes water from the surface. The atmosphere becomes saturated with water vapor, and clouds cover the planet in an unbroken shroud. Water vapor is itself a potent greenhouse gas, trapping even more heat and accelerating the warming process. High in the atmosphere, ultraviolet radiation from the sun breaks apart water molecules through a process called photodissociation. The water molecule splits into hydrogen and oxygen atoms. The lightweight hydrogen atoms, moving rapidly at the high temperatures prevailing in the upper atmosphere, escape to space. Earth is losing its water permanently. Oxygen from the split water molecules reacts with rocks on the surface, oxidizing iron and other elements. Some oxygen escapes to space as well. Over millions of years, Earth's oceans will completely evaporate and be lost to space, never to return. The water that made Earth unique among the terrestrial planets, the medium in which life arose and flourished for billions of years, will be gone. What was once a world teeming with countless ecosystems, from tropical rainforests to coral reefs to Arctic tundra, is now a barren, lifeless rock. The transformation from living world to dead planet is complete. The Sun, which nurtured life for so long, has become life's executioner. We must hope that by this time, humanity has learned to establish permanent settlements on other worlds, perhaps in orbit around other stars in distant parts of the galaxy. We advance further still, to a time 4.8 billion years beyond the present day. The Sun is now nearing the end of its main sequence lifetime, approaching 9.4 billion years of age. It is 67% more luminous than the modern Sun, blazing with an intensity that would be unbearable to witness from Earth's surface if anyone were still there to observe it. The Sun is slowly winding down, though it may not appear that way from the outside. The hydrogen fuel in the core is nearly exhausted. For billions of years, fusion reactions have converted hydrogen into helium, and now the core consists almost entirely of helium. Hydrogen fusion continues in a shell surrounding the core, but conditions in the core itself can no longer sustain the fusion of hydrogen. Without fusion in the core to generate outward pressure, the helium core begins to contract under its own gravity. As it contracts, gravitational energy is converted to heat, and the core grows hotter even as fusion within it has ceased. This seems counterintuitive, but it is a consequence of the virial theorem in astrophysics. For a gravitationally bound system, half the energy from contraction goes into thermal energy, heating the material, while the other half is radiated away. The heat from the contracting core flows outward into the surrounding hydrogen-rich layers. These layers heat up, and hydrogen fusion in the shell accelerates. The increased fusion rate causes the outer layers of the Sun to expand and cool. The Sun is beginning its transformation into a red giant, though this process will unfold over hundreds of millions of years. If you could stand on Earth's scorched surface and look up at the Sun during this era, you would see a bright reddish-orange sphere appearing about 1.5 times the diameter of the full moon. The sun's surface temperature has dropped to around 4,000 degrees Celsius, giving it a distinctly reddish hue compared to the yellow-white color we see today. The dimming of surface temperature is more than compensated by the increased surface area, resulting in much greater total energy output. Unfortunately, even if humans or their descendants survived to this era, Earth itself would be utterly uninhabitable. Surface temperatures hover around 300 degrees Celsius, hot enough to melt lead and zinc. Earth has become like the inside of a pizza oven, a hard, desiccated rock devoid of water, atmosphere, or any form of life. Looking directly at the sun, even briefly, would cause immediate and permanent blindness. No atmosphere remains to scatter and diffuse the light, and the sun's intensity at these wavelengths would damage tissue instantly. As the sun approaches the end of the main sequence, it enters the subgiant phase. The helium core has grown massive, containing the mass equivalent to approximately 140 Jupiter-mass objects, though compressed into a volume smaller than Earth. The core has reached a critical point. Temperatures exceed 100 million degrees Celsius, and pressures are unimaginable. The core is so dense that matter begins to behave according to quantum mechanical principles. Electrons are compressed so tightly that they enter a state called electron degeneracy, where quantum mechanics prevents further compression. The heat from the contracting core reaches the hydrogen-rich shell surrounding it, and hydrogen fusion in this shell intensifies dramatically. The shell burns fiercely, releasing tremendous energy. Over the next 500 million years, this shell burning causes the sun's luminosity to increase exponentially. The sun becomes 34 times as luminous as today, then hundreds of times brighter, and eventually thousands of times more luminous than the modern sunday. Earth, if it still exists as a coherent body, experiences temperatures far beyond anything imaginable. If any solid surface remained, you could theoretically sail a boat on waves of molten aluminum and copper, which would be liquid at these temperatures. Of course, no boat could survive such conditions, and no human could witness this hellish scene. This is purely a thought experiment to illustrate the extreme conditions. Another 85 million years pass, and the sun reaches 2,300 times its current luminosity. The enormous energy output causes the sun's outer layers to expand dramatically. The sun has become a true red giant, with a diameter exceeding 200 times its main sequence size. The photosphere extends beyond the orbit of Mercury, and possibly even beyond Venus. Earth faces complete destruction. The most optimistic scenarios suggest Earth might be reduced to its iron core, stripped of all overlying material. More likely, Earth will be vaporized entirely, its atoms dispersed into the expanding envelope of the red giant. Either way, Earth as a discrete object ceases to exist. The planet that was humanity's home for countless generations is no more. Mercury and Venus suffer similar fates, consumed by the expanding red giant. These inner planets, scorched and barren even under the normal sun, are obliterated as the sun swells. The intense radiation and stellar winds strip away their rocky mantles, and they vanish into the star's outer layers. The outer planets fare better, at least temporarily. The increased solar radiation will erode the atmospheres of Jupiter and Saturn. Powerful stellar winds blast away at the upper atmospheres, stripping away hydrogen and helium over millions of years. However, Jupiter and Saturn are so massive that they likely retain substantial atmospheres even after significant erosion. Jupiter has a good chance of surviving both red giant phases that the sun will experience. Interestingly, the sun's transformation into a red giant might render some previously frozen worlds habitable, at least temporarily. Saturn's largest moon, Titan, is currently a frozen world with a thick atmosphere of nitrogen and methane, and lakes of liquid methane and ethane on its surface. Surface temperatures hover around minus 180 degrees Celsius. As the sun's radiation intensifies, Titan warms dramatically. The methane and ethane evaporate, and the water ice that makes up much of Titan's mass begins to melt. Titan could develop liquid water oceans mixed with ammonia and other compounds. For a few million years, Titan might have conditions reminiscent of early Earth, with liquid water, a thick atmosphere, and abundant organic chemistry. Whether life could emerge and develop in such a brief window is unknown, but it is a fascinating possibility. Even more remarkably, distant Pluto could be transformed. Currently a frozen dwarf planet orbiting in the outer reaches of the solar system with surface temperatures around -230 degrees Celsius, Pluto would warm to temperate conditions under the red giant Sunday. Its frozen nitrogen and methane would melt and evaporate, forming a temporary atmosphere. The water ice beneath might melt, creating liquid water oceans. For a brief cosmic moment, Pluto could be a tropical paradise, though any paradise would be fleeting on astronomical timescales. At this stage, the Sun is consuming nuclear fuel at an astounding rate. It burns more fuel in 6 million years than it did during its entire 10 billion year main sequence lifetime. This furious burning cannot be sustained for long. The helium continues to accumulate in the core as the hydrogen shell burns around it. The helium core grows more massive and contracts further under its own weight. The core becomes super dense, with matter packed so tightly that a teaspoon of core material would weigh several tons on Earth. Despite the extreme density, the core is supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. The core is now what astronomers call a degenerate core. Temperatures in the core continue to rise as contraction releases gravitational energy. Finally, after millions of years of building pressure and temperature, the core reaches approximately 100 million degrees Kelvin. At this critical temperature, helium nuclei possess enough kinetic energy to overcome their electromagnetic repulsion and collide with sufficient force to fuse. Then something astonishing happens. This event is called the helium flash, one of the most dramatic moments in the life cycle of a sun-like star. The helium ignites not gradually, but explosively. Within seconds, the energy released equals the entire luminous output of all the stars in the Milky Way galaxy combined. For a brief moment, the sun's core generates more energy than 100 billion normal stars. Why does the helium ignite so explosively? The answer lies in the unusual properties of the degenerate core. In a normal gas, if temperature increases, the gas expands and cools, creating a negative feedback that stabilizes the system. But in degenerate matter, pressure depends on density, not temperature. When helium fusion ignites and temperature soars, the core does not expand and cool. Instead, the higher temperature accelerates fusion even more, and a runaway reaction occurs. The helium flash releases an enormous amount of energy in an extremely short time, perhaps just seconds. However, most of this energy goes into lifting the core out of its degenerate state rather than being radiated away. The energy heats the core so intensely that it vaporizes the degenerate matter. The core expands and cools rapidly, and fusion rates drop to a sustainable level. Within minutes, the core has transitioned from a degenerate state to a normal gaseous state, and helium fusion proceeds at a stable rate. From the outside, surprisingly little changes. The enormous energy of the helium flash is absorbed in the core and does not reach the surface. The red giant dims slightly, but does not explode or undergo any visible catastrophe. An external observer would barely notice that anything dramatic had occurred inside the star. The helium flash transforms the sun fundamentally. The core is no longer degenerate, and it now fuses helium into carbon through a process called the triple alpha process. 3 helium nuclei combine to form 1 carbon nucleus. The energy release stabilizes the core, and the sun enters a new phase of its life. Over approximately 10,000 years, the red giant shrinks dramatically and dims to less than 2% of its peak luminosity during the red giant phase. The sun is now about 10 times the diameter of the current main sequence sun, and roughly 40 times more luminous. Compared to the peak of its red giant phase, it is a mere shadow of itself. but it remains far larger and brighter than the main sequence Sunday. The Sun has become a horizontal branch star, so named because stars in this phase occupy a roughly horizontal region on the Hertzsprung-Russell diagram, a chart astronomers use to classify stars. The Sun now has a distinctly orange-yellow color rather than red. Its surface temperature has increased from the cool 3,000 degrees of the red giant to around 5,000 degrees. The appearance would be dramatic if any witnesses remained. The Sun dominates the sky of the surviving outer planets, appearing as a huge glowing disk. The Sun settles into a new equilibrium, and there is a strange sense of déjà vu. What happened with hydrogen billions of years ago is now happening with helium. The core fuses helium into carbon at a steady rate, releasing energy that supports the star against gravitational collapse. A hydrogen-burning shell continues to operate outside the helium-burning core, converting hydrogen to helium and adding to the helium supply available for core fusion. This phase lasts approximately 100 million years, a brief interval compared to the Sun's 10 billion-year main sequence lifetime. During this time, the Sun burns helium at an incredibly high rate, consuming fuel about 100 times faster than it burned hydrogen during the main sequence. The Sun is living fast and will die soon, relatively speaking. As helium fuses in the core, it produces carbon and oxygen. The core gradually transforms from helium to a carbon-oxygen mixture. This carbon-oxygen core grows in mass as fusion continues. The helium is consumed rapidly, and the Sun's time as a helium-burning star is limited. Finally, 12.1 billion years after its formation, the Sun exhausts all the helium in its core. Helium fusion ceases in the center, but continues in a shell surrounding the now inert carbon-oxygen core. The core begins to contract under gravity once again. As before, contraction releases heat, and the core temperature rises even though fusion has stopped there. The Sun begins its second ascent up the red giant branch. This time, it will grow even larger than before. The helium shell burns furiously, and a hydrogen-burning shell operates outside the helium shell. Both shells dump enormous amounts of energy into the overlying layers, causing them to expand dramatically. The Sun swells to truly gigantic proportions. The Sun becomes a red giant for the second time, but now with a carbon-oxygen core. The core continues to contract and heat up under gravity. You might expect that eventually the core will become hot enough for carbon to fuse, perhaps triggering a carbon flash, similar to the helium flash. However, for stars of the Sun's mass, this does not occur. Carbon fusion requires temperatures exceeding 600 million degrees Celsius. Despite the high pressure in the contracting core, the Sun's mass is insufficient to compress the core to such extreme temperatures. The core again becomes degenerate as quantum mechanical effects prevent further compression. Temperature rises, but never high enough to ignite carbon fusion. The Sun reaches a maximum luminosity, perhaps 3,000 times greater than its current value. The outer envelope expands to a truly staggering size, possibly extending beyond the orbit of Mars, perhaps even reaching Jupiter's orbit. The Sun has become an asymptotic giant branch star, one of the largest and most luminous types of stars. The high temperatures in the core and shells heat the outer layers immensely, causing them to expand to enormous volumes. The Sun's radius may exceed 200 million kilometers, more than 300 times its current size. If placed at the center of the current solar system, the Sun would engulf Mercury, Venus, Earth, and Mars completely. Its outer atmosphere might even reach Jupiter, some 800 million kilometers from the center. What about Mars? Throughout both red giant phases, Mars orbits precariously near the expanding Sunday. Scientists have calculated that Mars has a reasonable chance of surviving, though it would be subjected to extreme heating and intense radiation. The Martian surface would be scorched and any remaining atmosphere blown away, but Mars might remain intact as a solid body, orbiting the bloated red giant at close range. The expanded outer envelope of the Sun is very tenuous, with densities far lower than Earth's atmosphere at sea level. the material is more like a hot vacuum than a solid or liquid. Yet these tenuous outer layers contain a significant fraction of the Sun's total mass, perhaps half of it. This material is only loosely bound to the core by gravity. The core itself has become extraordinarily dense. The carbon-oxygen core is now a white dwarf in all but name, compressed to Earth size or smaller, despite containing a significant fraction of the Sun's original mass. The core and outer envelope are increasingly decoupled, almost like two separate objects barely connected by a tenuous intermediate region. Soon, the core and outer layers begin to separate violently. The details of this process are complex and not fully understood, but observations of other stars suggest it involves a series of spectacular thermal pulses and mass loss episodes. Every few thousand years, the helium-burning shell experiences an instability, causing a sudden, intense burst of fusion. This pulse of energy heats the overlying layers and drives powerful stellar winds that blow material away from the star. In a series of eruptions occurring over perhaps 100,000 years, the outer layers of the Sun are flung away from the core and dispersed into space. Roughly half the Sun's mass is expelled in these outbursts. The material expands outward at speeds of tens of kilometers per second, eventually spreading throughout the inner solar system and beyond. This material, enriched in carbon, nitrogen, and oxygen from nuclear fusion, will one day be incorporated into new generations of stars and planets, continuing the cycle of stellar birth and death. The remaining half of the Sun's mass is not expelled, but falls inward onto the dense core. The core accretes this material, growing more massive. The infalling material heats up as it settles onto the core, and the core becomes increasingly hot and luminous. The Sun's appearance transforms dramatically during this phase. It shifts from the reddish color of a cool giant star to an intense white-hot glow as the core is revealed. The surface temperature of the exposed core exceeds 100,000 degrees Celsius, roughly 20 times hotter than the current Sun's surface. At these temperatures, the core emits most of its radiation in the ultraviolet part of the spectrum, invisible to human eyes but carrying enormous energy. The transition from red giant to exposed white dwarf occurs relatively rapidly, perhaps in just 10,000 years or so. This is barely an instant in astronomical terms. The Sun has become a planetary nebula, though the term is misleading since planetary nebula have nothing to do with planets. Early astronomers viewing these objects through primitive telescopes thought they resembled planets and gave them this unfortunate name. The intense ultraviolet radiation from the hot core ionizes the expanding shell of gas surrounding the star. The gas absorbs ultraviolet photons, and electrons are stripped from atoms. When electrons recombine with atoms, they emit visible light, causing the nebula to glow in brilliant colors. Oxygen emits green light, hydrogen glows red, and nitrogen produces deeper reds. The result is one of the most beautiful sights in the universe, a glowing shell of gas surrounding a brilliant white central star. If the violent mass loss occurred all at once, the Sun would lose a significant fraction of its mass rapidly, and its gravitational pull on the remaining planets would weaken substantially. Planets might be flung into deeper space or escape the solar system entirely as the Sun's gravity diminished. However, observations indicate that mass loss occurs gradually over hundreds of thousands of years, not instantaneously. The remaining planets from Jupiter outward to the Kuiper Belt stay gravitationally bound to the Sun throughout this process, though their orbits shift outward as the Sun loses mass. The weakened gravity cannot hold them as tightly, so their orbital radii increase. Jupiter, Saturn, and any remaining outer planets continue to orbit the remnant Sun, now separated by even greater distances than before. Mercury and Venus were consumed during the Sun's first red giant phase. Earth was probably destroyed as well, though some models suggest it might barely survive, perhaps as a scorched iron core with all lighter elements stripped away. Mars has a decent chance of surviving both red giant phases and remains in orbit around the white dwarf, though it has been transformed beyond recognition by the intense heat and radiation it endured. The exposed core, now a white dwarf, is extraordinarily hot, with a surface temperature around 170,000 degrees Kelvin. It shines with a luminosity approximately 4,000 times greater than the current Sun, despite being no larger than Earth. The white dwarf emits primarily ultraviolet radiation, making it appear blindingly bright in UV, but relatively dim in visible light. The energy radiating from the white dwarf illuminates the expanding shell of gas around it, creating a spectacular planetary nebula. These nebulae display intricate structures, with shells, rings, and filaments of glowing gas shaped by stellar winds and magnetic fields. Each planetary nebula is unique, reflecting the specific history of the star that created it. The Sun's nebula will be similarly beautiful and complex. But this magnificent display is fleeting. The planetary nebula phase lasts only a few tens of thousands of years. The expanding gas shell continues to spread outward and dissipate, becoming more diffuse with each passing millennium. After perhaps 50,000 years, the gas has spread so thin that it no longer glows visibly. The nebula fades and dies out, merging with the interstellar medium. What remains is the white dwarf, a dense stellar remnant containing most of the Sun's original mass compressed into an Earth-sized sphere. The white dwarf is now about 200,000 times more dense than the Sun is today. A sugar cube-sized piece of white dwarf material would weigh about 10 tons on Earth. This extreme density is supported by electron degeneracy pressure, the same quantum mechanical effect that supported the degenerate cores earlier in the Sun's evolution. The white dwarf is initially extraordinarily hot from the energy of gravitational contraction and the heat left over from the fusion era. But the white dwarf has no internal energy source. Fusion has ceased permanently. The white dwarf cannot generate new energy, so it will simply cool off over time, radiating its stored thermal energy into space. This cooling process is remarkably slow. White dwarfs are small, and their surface areas are tiny compared to normal stars. Despite their high temperatures, they radiate energy away gradually. The white dwarf will spend billions of years cooling down, slowly dimming and shifting from white to yellow to orange to red as its surface temperature drops. The oldest known white dwarfs in the Milky Way, formed from stars that died shortly after the Big Bang, have been cooling for approximately 12 billion years. Even after all this time, they still maintain surface temperatures around 5,000 degrees Kelvin, similar to the current Sunday. These ancient white dwarfs glow with a faint reddish light, invisible to the naked eye from any significant distance. Whichever planets survive the Sun's red giant phases will orbit the white dwarf for billions of years more. They will receive little heat from the dim white dwarf, and temperatures throughout the outer solar system will plunge to just a few degrees above absolute zero. Any remaining worlds will be frozen solid, utterly dark and cold, lit only by the faint glow of the white dwarf and distant stars. Over tens of billions of years, the white dwarf will continue to cool until its surface temperature approaches the temperature of the cosmic microwave background, just 3 degrees above absolute zero. At this point, the white dwarf will have become a black dwarf, a cold, dark stellar remnant that emits virtually no radiation. However, this process takes so long that no black dwarfs exist yet in the universe. The universe itself is only 13.8 billion years old, insufficient time for even the oldest white dwarfs to cool completely. Eventually, perhaps in 100 trillion years, the Sun will become a black dwarf, a cold crystalline sphere of carbon and oxygen drifting through the darkness of space. The planets, if any remain, will orbit this dark relic in perpetual night. The solar system will be a cold, dead place, all traces of its vibrant past erased by the passage of unimaginable spans of time. This is the complete history of our Sun, from its birth in a collapsing gas cloud 4.6 billion years ago to its ultimate fate as a cold, dark cinder in the incomprehensibly distant future. The Sun that has nurtured life on Earth for billions of years will one day destroy that life and ultimately fade into darkness. Yet even in death, the sun will have fulfilled a cosmic purpose. The heavy elements forged in its core through nuclear fusion will be dispersed into space, providing raw materials for future generations of stars and planets. The cycle continues eternally, birth and death, creation and destruction throughout the cosmos.